Good morning, good afternoon, and good evening. My name is Sian Lim. I'm the lead PI. On behalf of my team, I'm presenting a progress report on a competitive research program funded by the National Research Foundation of Singapore on valorization of pathways using enzymatic and microbial engineering. We are a multidisciplinary team based on NTU as the leading institution, together with A-STAR and NUS with collaborators from Imperial College London and Nottingham University in the UK. The program consists of two parts, where in part one, we aim to produce pathase variants with considerably higher activity than the wild type to convert pathways into its monomer, TPA and EG. And in part two, we plan to install synthetic metabolic pathway to enable the uptake and conversion of the TPA and EG into value-added molecules such as oil, cellulose, or any other molecule of interest. Carbon neutrality is proposed to be achieved by incorporating the carbon dioxide sequestering cyanobacteria. I am presenting a progress report for the 18th month, and due to the timing requirement by NRF, the data reported is only up to 14 months. To establish the baseline in the first phase, we perform a reaction with PET substrates of different formats and different crystallinity using two different wild-type enzymes, one from Eodonella sakaiensis PET hydrolase, abbreviated IS PETase, and leaf branch compost cutinase, abbreviated LCC. The PETase reaction is run 30 degrees over 3 days, and for the LCC is performed at 70 degrees over 1 day. Both enzymes show very similar trend. The rate is faster when the PET substrate is amorphous or less crystalline, and on the ground or micronized PET, where allowing high surface area and volume ratio. However, obviously we see here it does not translate directly to the post-consumer waste PETase or in the sheet format. So our goal here is really to increase or degradation using the PETase from 20% to as high as we can, and run it for 30 degrees for as long as we can. So which means that we need a better PETase. We started by increasing the thermostability of the PETase, and the benefit is expected to be twofold. It will last longer in the reaction. It will also assist in the screening. And we actually managed to do that by forming a cyclic PETase using the Spitex spike catcher. And we found that the PETase is thermostable with melting point of about 70 degrees Celsius. We have also confirmed that despite incubation at 70 degrees for 10 minutes, the TC PETase remains in solution and show higher than 50% activity remains after the treatment. We have filed an international patent for these. TC PETase is the first demonstration of a novel, highly stable, thermostable cyclic PETase. It is expected to provide longer lifetime of the enzyme at the reaction condition, with potential application of PET hydrolysis at higher temperature. And in addition to that, we have also benefit for facilitating screening, allowing us to do heat treatment. So using this TC backbone, we generated a library of random mutation, and using the proxy substrate, we screened about 4,000 variants. We have 9 hits so far, and 4 times higher improvement compared to the wild type. And of course, the activity that we have done here all are on proxy substrate, and we need to confirm that the activity is also true for the PET substrate. So we have engineered PET microparticle here with the mean diameter of about 40 microns. And the idea here is we would like to be able to also use this PET microparticle for future high throughput screening. By loading oligo inside this PET microparticle, upon degradation, we would be able to use the oligo in a PCR reaction where we can identify high performing PETase. What we would like to show here is also that by PETase treatment, we can see a good degradation of the microparticle as well as the surface erosion on PET films. By loading this oligo particle in the microparticle, we can enable future high throughput screening using this method. As a benchmark comparison, the TC PETase is the most thermostable so far. It retains more than 50% of its activity after heat treatment at 70 degrees for 10 minutes. There are no other variants that has been reported so far with activity over 50 degrees Celsius using proxy substrate. Most of the PET microparticle that has been has been synthesized are typically in the nanometer range, and they are used as microplastic models and tracers in animal models, but no one have actually used it for development of high throughput screening for identifying the best performing peptides. What is interesting also in the literature is that all the reports have been using on varying PET substrate, using powder, microbeads, films, and various different crystallinity, which make us very challenging to compare what peptide, whether the peptide is performing better than the others. So again, we need to establish the standardized peptide assay, and we are working toward that for future correlation with PET bottles as well. We also would like to update the project 2 to 4 on microbial engineering. We have done the engineering on 3 different microbes, 2 species of cyanobacteria, 3 species of cellulose bacteria, and 2 species of yeast. Most of the PET utilization modules, or we call PUMs, have been constructed for all these 3 different microbes. And we have also determined the tolerance to EG as well as TPA for these microbes, and they can tolerate quite in the millimolar range of these substrates. And this is a summary of the progress we have made in year 1. Just to summarize, we have constructed 2 libraries of mutants peptides on linear as well as cyclic peptides. We have standardized the assay for the proxy as well as PET substrates. We have synthesized the microparticle. We have completed the construction of PUMs for EG and TPA in 3 different types of microbes. We have filed a patent for the TC peptides as well. And we are in the progress of screening more mutants. And we are testing the PET microparticle using peptides and optimizing the synthesis protocols. And we're starting to install the PUMs into native microbes and the checking functionalities of these synthetic metabolic pathways. We have also submitted a mini review for looking at the relationship between substrate and peptide activity. Of course, going into the year, the remaining of year 2, 3, and 4, we plan to develop emotion-based high throughput screening platform for screening of 1 million clones for each library. We aim to develop scale-up production, and we hope to file an IP on the strains that can actually convert PET degradation product into value-added molecules, including the bioprocess for future industrial applications. We have been faced with some challenges, and one of them is the delay in developing the high throughput screening platform, mostly because of the leakiness of the microparticle that is being synthesized. And we can mitigate that by modifying the surfactant and developing the medium throughput platform using the TC peptides. There are some administrative challenges due to the pandemic, which really limit the access to the labs, particularly for A-Star. We are operating pretty much in half capacity for the last 6 months. And staffing, in terms of the limited employment path that is issued by the ICA, as well as the new installation of the hiring system, has put the project into some setbacks. But despite that setbacks and challenges, we have managed to achieve most of the 18 months deliverables, and we have reached at least the 4 times higher active enzymes that we can see based on our screening method, and we are confident that we can actually achieve 5 times. We also encapsulate oligonucleotides in an order of magnitude higher compared to what we had set out in the beginning of this project. And there are no changes that would affect the deliverables as we expected. We have some minor adjustments to the project in the development of medium throughput instead of high throughput using proxy substrate. Again, this is a safety measure to start immediate screening, and then while we are waiting for the high throughput to be ready. And the project number 4, the end product will be changed from the polyunsaturated fatty acids to cannabinoids. This is actually a demonstration that we can benefit from the modularity of the synthetic pathway installation because of the shared intermediates. Some of the changes is that we have hired additional RFs as much as we can, and repurpose some of the RFs that are working on the project to ensure progress. And we will be hiring 2 more in the next coming year. The annexes will contain midterm deliverables for reference, as well as more details on each of the project. And thank you very much for your attention.